In section 9.3, we're going to be looking at matrices and systems of equations, and our objective is to solve systems of equations using matrices. Topic 1, we're going to talk about matrices and row equivalent operations. As you probably, hopefully, know, it doesn't take long before solving a system of equations via algebraic techniques gets to be really tedious, especially if you're working in the situations where there are 3 equations and 3 variables, or expand that into 4 equations and 4 variables or more. Most of the tediousness comes from having to constantly write down a lot of steps along the way. Mathematicians, always the bastions of brevity and laziness, invented a kind of shorthand notation for solving systems of equations that keeps track of only the coefficients, and the variables are just dead weight. This system is going to be based on matrices, which is the plural of matrix, and it allows us to manipulate these entire equations without writing down all the dead weight over and over. For example, if we take the equation 2x minus 3y equals 7 and 1x plus 4y equals negative 2, we can write this more simply as 2, negative 3, 7, and then 1, 4, negative 2, using just the coefficient values in each of our equations. In this matrix, each of the rows represents an equation, and each of the columns represents a variable or constant. The vertical line right here in this augmented matrix represents the equals sign in the equation. So that matrix up there is actually an augmented matrix. That's just the name for a matrix that contains not only the coefficients but also the constant term, and it has that vertical bar right there representing the equal sign. We can also talk about the coefficient matrix, where the coefficient matrix just has the coefficients of the variables and then does not have the equal bar. Sometimes your coefficient matrix will be set equal to a column matrix that has the solution that's just in a different notation. Other jargon that we need to know is that a matrix that is m by n has m rows and n columns. And the intersection of a row and a column is a number, or called an element in the matrix, or an element. And the main diagonal of a square matrix goes from the top left to the bottom right. This is our main diagonal in this square matrix here. Goes from top left to bottom right. Sorry, top left there to bottom right. Our next topic, we're going to look at Gaussian elimination with matrices. Using the techniques we developed in 9.2, we're going to make use of the streamlined matrix notation to perform some elimination. So remember that our goal in doing elimination is to transform our system into something that looks like this, where I can solve for a variable z, then substitute that back in to solve for y, substitute y and z back in to solve for x. What would this look like in matrix form? In matrix form, the top equation, A is the coefficient of x, B is the coefficient of y, C is the coefficient of z. I'm making an augmented matrix here, so I've got that vertical line for the equal sign, and D is the constant. Around the outside of a matrix are these bracket symbols. When I get to the next equation, it does not have any x, so I do need to put in a 0 for the coefficient of x, then E for the coefficient of y, F for the coefficient of z, G for our constant. And in the bottom row, there are 0x and 0y. H is the coefficient of z, and then k is the constant. So this would be the matrix that matches up with this system of equations here. Okay, we're going to solve the following system, starting by writing the system as an augmented matrix. So let's look at our three equations here. This first equation has a coefficient of x that is 2, a coefficient of y, -1, z is 4, and then equals -3. That's the top row of our matrix. In the next equation, the coefficient of x is 1, the coefficient of y is -2, and the coefficient of z is -10. And then I have -6 for the constant. In the last equation, the coefficient of x is 3. There's no y term, so the y coefficient is 0, and the z coefficient is 4 with a constant of 7. Since each row is really an equation, we can always do the following to an augmented matrix without changing the results. We can interchange any two rows, which just means flipping two equations. We can multiply each row by the same number, that's just multiplying an equation by the same number on both sides. And I can add one row to another, any multiple of one row to another. That's one of the things that we do in the elimination method towards solving an equation. So using the augmented matrix above, we can perform the following row equivalent operations on this page here to write this matrix in what is going to be row reduced form. Note that the steps that we are asked to take here are provided for us. These will not be steps that you're going to need to come up with on your own. These are steps that we're providing right here to demonstrate how this process is working, but it's not something that you are going to have to be able to do solely on your own in a by hand manner. Okay, so let me take that original matrix real quick. 2, -4, -3, 1, -2, -10, -6, 3, 0, 4, 7. And we are going to interchange row 1 and row 2. So we're going to swap row 1 and row 2. The reason for that is because there is a 1 coefficient here. The reason doesn't matter right now. We're just going to follow the directions. So we're going to put row 1 on top. We'll have 1, -2, -10, -6. Then 2, -1, 4, -3, and we're going to leave our 3, 0, 4, 7 alone. Okay. The next step says we're going to take the new row 2. So I'm going to make myself a note down here. Row 2 is going to be equal to -2 row 1 plus row 2. And I'm also going to do a new row 3 equal to -3 row 1 plus row 3. All right. So row 1 isn't going to change. That's going to stay 1, -2, -10, -6. But rows 2 and 3 are going to change. For row 2, I'm going to take -2 times row 1 and add it to row 2. -2 times 1 is -2. -2 plus 2 is going to be 0. -2 times -2 is 4. 4 plus -1 is 3. -2 times -10 is 20. 20 plus 4 is 24. -2 times -6 is +12. +12 minus 3 is 9. On to row 3. -3 times 1 is -3, plus 3 is 0. -3 times -2 is +6, plus 0 is +6. -3 times -10 is 30, plus 4 is 34. And -3 times -6 is +18. +18 plus 7 is going to be 25. Now, as far as why this is done, again, you're not responsible for the whys right here, but what I need to do is I'm trying to get something that is of the form ABCD 0, EFG 00, HK. So we have just created these two zeros. So that's what we're trying to do here to get it in that form that's going to be solvable. We're going to continue just following these directions and seeing how this is going to allow us to solve the matrix. The next step, we're going to take new row 2 as a third of row 2. So we're going to divide by 3. So row 2 is going to equal 1/3 of row 2. And I can do that here. So I have 1, -2, -10, -6 stays the same. 0 divided by 3 is still 0. 3 divided by 3 is 1. 24 divided by 3 is 8. And 9 divided by 3 is 3. And we're going to leave our 0, 6, 34, 25 alone. Okay. Continuing, the next step says take new row 3 as -6 row 2 plus row 3. So no change to row 1. 1, -2, -10, -6. No change to row 2. 0, 1, 8, 3. And then no change, or no, yes change to row 3. Row 3 is going to be -6 of row 1. So 0 times -6 is still 0, plus 0 is still 0. That I'm going to have -6 times 1 is -6. And -6 plus 6 is 0. -6 times 8 is -48. -48 plus 34 is -14. And then -6 times 3, that's -18. Plus 25 is 7. All right, and then our last step here is to take row 3, and looks like we're dividing it by -14 of row 3. So the top row stays the same, 1, -2, -10, -6. Middle row stays 0, 1, 8, 3. And the bottom row, 0 divided by 14 is 0, 0 divided by 14 is 0. When I have that -14 here divided by -14, that's 1. And then 7 divided by -14 is -1/2. Okay, so we've done some work on this matrix to rewrite it in this form. This is already printed for you on the next page. So I'm going to flip over here and make sure that we have what we were expecting on the next page. The matrix that we just got should say 1, -2, -10, -6, 0, 1, 8, 3, 0, 0, 1, -1/2. This matrix is equivalent to the one that we started with, and it's going to allow us to solve for the solutions of x, y, and z. Notice at the bottom row right here that has 0, 0, 1, -1/2 would be read as 0x plus 0y plus 1z equals -1/2. So this bottom row tells us that the z value is -1/2. In the next row, this reads as 0x plus 1y plus 8z, which I now know is -1/2, is equal to 3. So that's y minus 4 equals 3. So I can solve and find that y must be 7. And then the top row, which reads as 1x minus 2y, which is 7, minus 10z, which is negative 1/2, is equal to negative 6. So that's x minus 14 plus 5 equals negative 6. That's going to allow me to solve and get an x value of 3. So I can solve and find the x, y, and z values once I get the zeros in this bottom portion and have ones along my main diagonal. So the important part of this notation is that my main diagonal contains only ones, and to the left of the diagonal are only zeros. So we've got our ones along the main diagonal, and to the left of that main diagonal, only zeros is what allowed us to be able to solve this. So our solution is the ordered triple where the x value is 3, the y value is 7, and the z value is negative 1/2. Now, if I was working on this matrix by hand, this is the type of step I would take. However, our calculators are even more efficient with this, and we can keep going. And if I was able to keep going and have not just a main diagonal of ones, which I did have before, and the lower half being zeros, which again I did have before, if I was able to also get the upper portion, the right portion, to be zeros, this is going to be even better because now the top line reads as 1x plus 0y plus 0z equals 3. The middle line reads as 0x plus 1y plus 0z equals 7. And the bottom line reads as 0x plus 0y plus 1z equals negative 1/2. So the solution, 3, 7, negative 1/2, is directly given to us inside of this matrix via these coefficient values. We have the solution for x, y, and z, instead of having to back substitute and solve for the y and x values. So this is definitely preferable in terms of the solution, and our calculators are going to be great at doing this. So this is the matrix in reduced row echelon form, or RREF for short. We'll want to know the RREF because that is how our calculator is going to know to take the matrix and put it in this form. Okay, so again, I already wrote the solution value up here, but this is read as the x value is 3, the y value is 7, the z value is negative 1/2. Okay, so I'm going to take a look at a calculator real quick. Let me go back to our original matrix so I can see that here. And on my calculator, if I'm not in the Decimals Grapher, but I'm on the regular decimals.com site, and I go into Math Tools, aside from the graphing calculator, I can select to use the matrix calculator. It is decimals.com/matrix. You could also just type that in. And I'm going to enter a new matrix. This matrix needs to have 3 rows and 4 columns. So I'm going to increase the number of rows and columns. And I'm going to enter my coefficients. So 2, you can use the tab key, -1, 4, -3, and then 1. That was an incorrect y here. The variable should not have shown up, so my apologies there. Didn't notice that I had done that. It's just coefficients that are in the matrix. So this is -2, -10, -6, and then 3, 0, 4, and 7. I think I hit the negative key instead of a 0 here, so let me go back and fix that one. There we go. Make sure I hit those keys correctly. We're going to hit enter on our matrix. It's going to establish that matrix. And now we want to solve this matrix. We would like to get it in row reduced echelon form, RREF. There is a button here where I can click on RREF of this matrix. So it's called matrix A. And I have the matrix in its row reduced echelon form. I can even turn it back into fractional form, and then it matches exactly with what I see in my paper here. 1003, 0107, and 001, -1/2. So this is how we are going to be solving these matrices. I did work through one of them by hand to get it into the RAF format to see what the process behind the scenes is. But for the most part, if we're setting things up in matrix format, we're setting this up for maximum efficiency. And so we would like to use the calculator to do these, all of them. All of our matrix operations we want to do throughout the calculator. Okay. The final note on this page that I need to pay attention to is I need to make sure that if I solve using the calculator, that I know what systems that are dependent or inconsistent are going to look like in their row reduced echelon form, so in their RREF form. So let's talk about this. So if our system has one solution, our matrix is going to look like the previous one, where we're going to have ones along the main diagonal, and we're going to have zeros in the bottom and upper corners. And then we're going to have some numbers, A, B, and C, on the far column. That's what it will look like for one solution. If it is dependent, what's going to happen is we'll still have our something across the top. So this top could change a little bit. I'm actually not going to fill in these top two rows. What's going to happen for sure in the dependent case is that your bottom row is going to come out where there is no 1. It's going to come out as something like 0, 0, 0. And so this is giving us a 0 equals 0 statement where it's entirely true and you have multiple solutions. Whether those multiple solutions are all points on a line or all points on a plane is going to depend on what happened up here. If you have 2 rows that eliminate or just 1 row that eliminates, if 1 row eliminates, then you'll be able to write your system as a line. And if both rows eliminate, it'll be as a plane. The other possibility for an inconsistent system here, again, you'll have something across the top and middle rows, but what you'll notice is in the bottom row, you'll get something like 0, 0, 0, and then 1 there. The important piece about this is that the 1 is on the far column, meaning the solution value. I didn't draw the equal bar here because I was thinking calculators don't draw those in. Let me draw it in right here though. This is stating that 0 is equal to 1, and that is going to be false. And so the inconsistent case right here is our no solution case. So we want to be able to recognize when something doesn't happen, usual, typical, normal here, no solution versus the 1 solution. Okay, let's go ahead and use the calculator to solve a couple of examples. Example 2 here, we want to use the calculator to perform Gauss-Jordan elimination, which means to get this thing into reduced row echelon form. So this is just another way of asking me to get this into its reduced row echelon form. And find the solutions, if any. Start by writing the system of equations as an augmented matrix. The first equation is 2x, so 2 plus 1y, 1, equals 1. The next equation is 3x plus 2y equals -2. And this is just 2 variables and 2 equations, so I'm going to have 2 rows and 3 columns. Let's go into our matrix calculator. I'm going to make a new matrix here. And for this new matrix, I want 2 rows and 3 columns. We'll enter 2, 1, 1, 3, 2, -2. and we need to find the row reduced echelon form of matrix B. So this matrix reduces to 1, 0, 4, 0, 1, -7. Remember, on the calculator, it doesn't show where the vertical bar should be, but I know that it should be here. So I'm going to draw that back in. And this tells me that 1x is equal to 4, and 0x plus 1y is equal to -7. So I have a solution of 4, -7. So I know the solution to this system. Okay, we're going to try this again with example 3. In this equation, since we're not using x and y and z, we're using m, n, and t. We just need to be very careful that they are all in the same order. So m is going to be the coefficient that is in first position. So my first equation, there's 1m, 1n, 1t equals 9. In my second equation, 1m, -1n, -1t equals -15. In my third equation, 3m, 1n, 1t equals 2. We're going to enter a new matrix. It has 3 rows and 4 columns. Let's enter this. 1, 1, 1, 9, 1, -1, -1, sorry, -1, -15, 3, 1, 1, 2. That matrix is called C, so I'm going to do the row reduced echelon form of matrix C. This is equal to 1, 0, 0, 0, 0, 1, 1, 0, 0, 0, 0, 1. So before I start writing down solutions, I need to notice that that bottom row immediately is false, and so there is no solution to this system. So it's not going to be true that I can solve the top 2 rows since that bottom row is false. This tells us that 0 is equal to 1. 0x plus 0y plus 0z, that's 0, equals 1. So this is false, and this system has no solution. Okay, our last example just asks us to go back and look at some of the problems we did in 9.3 and then attempt to solve these using matrices. So I'm going to go back and grab a couple of those. We did examples 1 and 2. I want to look at it. I think it asked me to look at particular example 3, but I do want to look at 1 and 2. So I'm going to do that. So this is example 1 from section 9.2. I'm going to write this one down with a matrix. So example 1 here, this matrix, the x would be 1, y -2, z 3, and 11. Then 4, 2, -3, 4, and 3, 3, -1, 4. Okay. We had solved this in example 2, and we had gotten a solution of 3, -1, 2. Let's see what happens if we use this matrix. New matrix. 1, -2, 3, 11. 4, 2, -3, 4, and 3, 3, -1, 4. This matrix is called D, so we'll do row reduced form of D. 1, 0, 0, 3, 0, 1, 0, -1, 0, 0, 1, 2. This gives us the solution that the x value is 3, the y value is -1, the z value is 2. So once again, we're checking an answer that we had done by hand in section 9.2. When we had worked this one by hand, we came out with the solution 3, negative 1, 2. That solution of 3, negative 1, 2 matches the solution that we get from our matrix. One more I want to check because example 2 was dependent. If you remember, we got all points on this line are solutions. Let's just see how this one looks if we are to solve this one with matrices. So in example 2, let me write my matrix over here. Coefficients are 1, 1, 1, 7, 3, negative 2, 1, 3, 1, 6, 3, 25. Okay. So in the matrix calculator, make myself a new matrix. 3 rows, 4 columns, 1, 1, 1, 7, 3, negative 2, 1, 3, 1, 6, 3, 25. And let's get the reduced row echelon. This one is capital E. This comes out as 1, 0, 0.6, 3.4, 0, 1, 0.4, 3.6, and then 0, 0, 0, 0. Okay. We certainly have a 0, 0, 0, 0 line. We can see that that means that our system is going to be dependent. So 0 equals 0, it's true. So we have a dependent system, which means many solutions. And let's see if we can quantify what those solutions are going to be. If I look at the top line here, I have 1x plus 0.6z, 0y, 0.6z equals 3.4, 0x, 1y plus 0.4z equals 3.6. Okay. Now, remember back on the previous example, when I had gotten my true statement, I had these two equations that were in terms of y and z, and we said that they must be identical. And we decided when I took one of those equations that I could solve for either y or z. We have a choice. We could solve for either one of those. At the time, I chose to solve for z because dividing by 2 was just going to make the numbers a little nicer. I kept it as a fraction, but dividing by 5 would have also been fine. I could have solved for y and written my equation in terms of z instead. I'm going to come back to that idea here in a second. For this one, it has been written in terms of z since I have x and y in terms of z. So we might have to do just a little bit of work to show that our two answers are the same. But if I solve for x is going to be equal to negative 0.6z plus 3.4, comma y, I'm going to again subtract off, so negative 0.4z plus 3.6, comma the z value would be z. So that would be the way to express this solution in terms of z. I just want to show real quick that my solution from number 2 in 9.2 is the same thing. So let's take this equation right here. 5y plus 2z equals 18. And instead of solving for z, let's solve for y. So let's take this equation, solve for y. 5y would be equal to negative 2z plus 18, and I'm going to divide by 5. So y would be equal to, we go to the regular calculator now. I need negative 2 divided by 5, which is negative 0.4z. And then I need 18 divided by 5 plus 3.6. So can we see how that's the same thing that I would have here? The negative 0.4z plus 3.6 for y. So my solution values are matching up. We have the same thing. It was just written differently on my original solution because it is my choice when I'm solving by hand which of these two variables to solve for, and I just made a different choice. When the calculator solved for it, the choice was forced by the code to try to get ones first along the main diagonal. So when the calculator does something like this, where it's got a dependent equation, you're, I would say, always going to end up with an equation that is in terms of z instead of terms of y or x, because it's going to try to get the ones in x and y because those are first. If you did want to get this in terms of a different variable like y, just don't put z at the end. Order your columns so that they're x, z, y, for example, and you could come up with a solution in terms of another variable. But this is what it would look like, and then what my final answer would look like if the system was dependent.